It would help if I unmuted myself. Hello, everyone. I'm Mr. Chappa, and I will be your professor for this course. Normally, when I make videos, I will record videos of me at a whiteboard and upload them to YouTube, but I'm making an exception this time, and I may do it again in the future. I'm actually using Zoom right now because I want to share some files that I have on my laptop with you, files that I'm going to make available to you that you're going to use throughout this course. So let me go ahead and share that file so you can see it. In fact, second here. All right. Instead of just opening the file from my own laptop, I'm going to show you where this file is in the Canvas shell. Right now, there's not a whole lot in the Canvas shell. But by the time you're watching this, there may be more. I'm recording this on Friday, January the, what is it, 8th, Friday before class starts. But I just wanted to show you where I will load files for you to access with Canvas. It's pretty intuitive. It's under Files. Right now, there's not much there, just a folder for distribution tables. And inside of it will be 3 distribution tables that we'll use in the course. The first of which is the Z distribution. They're kind of in reverse order because they're in alphabetical order. The Z distribution, the T distribution, and the chi-square distribution. Now, depending upon your Statistics 1 background, you probably have only seen 2 of these 3. But there are some Statistics 1 classes where you actually get to things such as test for association, goodness of fit test, and therefore use the chi-square distribution. We'll be doing that from scratch when we get to chapter 7. But to begin our review of Statistics 1, I want to open up this Z distribution. And let's actually download it. My video is still on. I'll go ahead and stop it just so it's not in the way. There we go. Let's go ahead and just download this so that it exists outside of this browser. And it's still inside the browser. But that's okay. However you want to access it is up to you. What you know or don't know about the standard normal distribution depends 100% on the statistics. So I'm going to take it from scratch and show you what this table is and how I expect you to use it in this class. Now, I will go ahead and tell you that of the 3 tables we're going to use, this is the one that we're going to use the least. In fact, we'll use it primarily as we're reviewing Statistics 1. And if you're wondering, well, why are we reviewing it? Why are we using this if we're not going to use it in Statistics 2? It's because this table will be used as we review some concepts from Statistics 1 that will translate to Statistics 2, namely the concepts of estimating a population value using a confidence interval or testing a population value using a hypothesis test. So I'll be going back and forth between this. It looks like I got somebody joining me. Well, hello, Mr. Simpson. How are you?
I'm doing excellent, sir. How are you doing?
I'm doing great. I'm just recording a lesson for your class. You're welcome to stay here. I forgot that when I open up the Zoom session, everybody gets a message. But I'm going to be recording this and uploading it to class. So you're welcome to hang around, or you can just wait to see the link uploaded to Canvas. So it's your choice whether or not you like to stay. I am going to go ahead and mute you so that there's no background noise. You're welcome to hang around.
All right.
I'm sorry, Wesley, you were just about to say something and I just muted it. If you want to hop in the chat and throw it in there, that's fine. All right, so, okay, so this is pretty cool. Just so you know, Wesley, or anybody else that happens to be watching this right now, I am still building the Canvas shell, which you can read on the homepage on the Canvas page, or the homepage in Canvas. But everything will be there in time. All right, so what are we going to do for this first review from Statistics 1? Well, we're going to talk about the normal distribution, the standard normal distribution. And in order to do that, I'm going to use this whiteboard. And again, I want to reiterate that normally the instruction will be done at a regular whiteboard in a classroom, which I will record and upload to YouTube and then link in Canvas. But every once in a while, I will make a video using All right. Okay, So what do I mean by a standard normal distribution? Well, let me go ahead and get some text going here. Standard normal distribution. There's a lot of words in there, but without, for fear of reteaching all of statistics 1, we're just going to review some main and basic concepts. A normal distribution, well, first off, the distribution is a set of values and the probability of them happening. For example, if I were to roll a single die, there's only certain values that we can get. We'll call those X. If I roll a single die, I can get a 1, 2, 3, 4, 5, or 6. And if we talk about the probability of those values, capital P probability, assuming it's a fair die, each of those has a 1 out of 6 probability of happening. Or if you wanted to express them as decimals, you could, or fractions are just as good. But that's what's called a discrete distribution, namely because the number of outcomes is finite and countable, and there's gaps between them. For example, you can roll a 2, you can roll a 3, but you can't roll a 2.5. Now, there are some distributions where the values are continuous, meaning that they can assume any decimal in between. For example, let's say that we were measuring people's weights, and we wanted to know the probability of being in a certain weight class. We'll just put a P for probability over there. Well, the problem with putting weights is if I put something like 100 pounds and 101 pounds, you could fall between those two depending upon the accuracy to which we're measuring. So normally when you have a continuous variable where the values can assume any decimal, we have classes of values. For example, we might say between 100 and 101 pounds with the assumption that if you hit 101, you would go to the next one. Or we can make these classes a little bit wider. We could say something like between 100 and 110, 110 to 120, 120 to 130, so on. And again, we would have to clarify where you belong if you land exactly. For example, if you weigh 110, do you belong here? Do you belong there? Typically, when you hit the upper limit, you move to the second class. So somebody who is 110 exactly would land right there. But then we could calculate the probability of somebody falling in this weight range. For example, we could say, well, there's a 10% chance that somebody falls in here, and then a 15% chance that they fall in here, and then maybe a 13% chance. I'm just making up numbers here. All I know is that at the end, these should add up the sum. And if you're not familiar with sigma for sum, don't worry, we'll see it later. Should be 100% or as a decimal, 1. So what does this have to do with the standard normal distribution? Well, when you calculate probabilities of values that fall within a range of values and can be measured with unlimited accuracy because of decimals, as opposed to over here, there are no decimals when you roll die. But when you have, let me get my thoughts gathered. When you have a continuous distribution where your values can assume any decimal to however much accuracy you want, then you can't say things like, what's the probability you weigh exactly 100 pounds? When you have continuous values that are measured using decimals, it's technically impossible to be exactly one value because the measurement depends upon the accuracy of the tool that you're measuring with. Next time you step on a scale and it says you weigh a certain amount, that is not exactly how much you weigh. That is how much you weigh within a certain tolerance level, depending upon the accuracy and the precision of the device that you're measuring with. Currently, it is impossible to measure continuous values exactly because we're limited by the devices with which we can measure them. So there's always some inaccuracy. So instead of saying we weigh exactly a certain amount, we do pretty much what I did in this circle, that circled range there where it says, one second, folks, where it says 100 to 110. We would say something like, what's the probability that my weight, and we'll just call it X, is greater than 100. So we'll say 100 is less than X, but at the same time, less than 110. That we can measure theoretically, saying that what's the probability we fall in a range of values instead of landing on a specific value. And in this case, we could say something like 10%. Okay, So we're calculating the probability of something that we're measuring that is a decimal. And because it's a decimal, we can measure it with infinite accuracy theoretically. So instead of saying the probability we're equal to a number, we say the probability that we're in a range of numbers. And then there's a variety of ways to do it. You can say something like the probability that I'm between two numbers, or you can say something like the probability that I'm greater than a number. What's the probability my weight is greater than 150? Or I can say something like, what's the probability that my weight is less than 135? And by the way, the presence of the or equal to line is completely irrelevant when you're measuring decimals, because the only difference between that bottom probability and the bottom probability without that line is the absence of being exactly 135 pounds. But when you're measuring things continuously with decimals, it is theoretically possible to measure exactly 135 pounds, meaning that the probability that you weigh exactly 135 pounds is 0. So removing 135 pounds doesn't change the probability. So all of these would be the exact same problems if I made all of the inequalities loose inequalities in the sense they allow the values to be equal. All right, so anyway, so if you have a continuous distribution, a distribution of values that can be measured using an infinite amount of precision, in theory, we don't talk about their probabilities being equal to certain values, but rather within ranges of values. All right, so now that we got that, what is a normal distribution? Well, a normal distribution is just a distribution whose probability distribution, the bell curve. And the mean, which is, there's a couple of ways to represent mean. For a population, it's the Greek letter mu. Don't worry, I'll give you a list of all these variables. The mean would be in the middle. So a normal distribution is basically a bell curve. There are some books that define it as a curve that's symmetrical on both sides, and the left tail and the right tail flatten out to 0 as you go forever. That's not a sufficient definition, though, because I can draw a picture of something that is symmetrical, has the mean in the middle, and the tails go forever, but isn't a bell curve. I could draw something like this, which is symmetrical, the average is in the middle, and both tails flatten out. So to be a bell curve or a normal distribution actually means up, peak, down, and both ends flatten out as you go forever, theoretically. So that's all the normal distribution is. It's basically a bell curve. But what is a standard normal distribution? Well, a standard normal distribution is just a bell curve with a very specific mean and standard deviation. A standard distribution has a mean of 0, meaning that in a standard normal distribution, in other words, a standard bell curve, the center is always 0, and the standard deviation is 1. Now, I'm not going to review how to calculate standard deviation. I will remind you that the variable for population standard deviation is a lowercase sigma, which looks like a 0 with the hair. And of course, the variable for population mean is, and you know what, I'm going to go ahead and write these variables on the next page. Let me type in here. Population mean, population standard deviation. I'm not very good at typing, by the way. And while we're at it, sample mean and sample standard deviation. These are all variables that in theory have been discussed in statistics 1, so I'm hoping as I write these, they are just a review. But the variable for population mean is the lowercase Greek letter mu, which if you spell it out as mu, but it looks like this thing right here. The variable for population standard deviation is a lowercase sigma, which is a circle with the hair. Sample mean, let me spell sigma a little bit better. Sample mean is x bar, which is just an x with a bar over it, and that's how you pronounce it, x bar. And sample standard deviation is a lowercase s. Mean is synonymous with average. Well, That's not 100% true from a theoretical perspective, but for our purposes, anytime you see the word mean, it just means average. Now, why do we have a variable for one for a population, one for a sample? Well, because in statistics, half, I would argue more than half, of statistics is called inferential statistics, where you are trying to make a claim about a population or say something about a population, but because the population is so large or dynamic, it's impossible to measure it. So we measure something from part of the population called a sample, and based on those sample measurements, we say things about the population. So it's important to have variables to represent the same concept, one for the population, one for the sample. All right, so anyway, a standard normal distribution is just a bell curve, and I'm going to put these in boxes because they're kind of important. But a standard normal distribution is just a bell curve where the average is 0 and the standard deviation. Now, there are ways we can illustrate the standard deviation on the bell curve, but I'm not going to worry too much about it since we're not going to talk about empirical. Okay, so this is cute and all, but what does any of this have to do with this distribution table? Well, this standard normal distribution table, which I will usually just call the Z chart because of the Z in the upper left-hand corner, is a table that lists the areas under a bell curve to the left of a given Z-score. And it's really pretty easy to use. Now, you may have not used a table before. You may have used technology to calculate Z-scores, but I don't want to require everybody to have the same technology because that's just an extra expense I don't want to incur on you. So instead, we're going to use a Z distribution table as much as possible. There's a way to use Microsoft Excel, which is what I use to generate that table. But we're just going to use a table which I will make available to you and will be available during quizzes and tests. We're not going to get into great detail about what a Z-score actually is right now, but let's just say that we have a standard normal distribution. Means it's a bell curve with 0 in the middle. And I give you a Z-score like Z equals 2.74. And I set up boundary and I shade the left side of it. We're going to be shading lots of pieces of bell curves this semester. It's not hard to do. But most of what we're going to do with those is figure out what is the area to the left. Now, the important thing about the area here, and this is worth typing, cumulative area to the left of Z equals 2.74, same as the probability that Z is less than 2.74 in a standard normal distribution. In other words, area equals probability. That's supposed to be an equal sign. I didn't let go of the shift key. So whatever this area is, oops, didn't mean to turn that. Oh. Sometimes I'll have this issue where I'm jumping around and things just go crazy on me, but I've worked with Zoom enough to figure out how to fix that most of the time. All right, so anyway, as I was saying, whatever this area is, it equals the probability that Z is less than 2.74. So we will be using areas under curves to represent probabilities. So what exactly is that area? Well, there's a way to get it using technology, but there is also a way to get it using this table. Let me show you the table, and then I'll go back to the problem. This table has Z-scores split into two parts. On the left are the digits to the left and right of the decimal, and on the top is a two-digit number representing the second decimal place. The numbers in the middle represent left areas of a given Z-score. Let's take a look at the Z-score that we have. The Z-score we have is 2.74. What we're going to do is we are going to go to the Z table right here, and we are going to look up 2.74 on the left column in top row. Now, if you notice, the first page has negative z, so we need to scroll into the page which contains the positive z's. And we're going to start by looking for 2.7, since that's the numbers to the left and right of the decimal of the z we're looking for. This is the row that we need to look at, the 2.7 row. Now, for the column, we need the second decimal digit, and the second digit in our z-score was the 4 right here. So going back to the distribution table, in this row, we need to look under the 0.04 column. Now be careful, it's not the fourth column. Fourth column is actually 0.3. The reason it's not the fourth column is that the first column is at 1 and 0. So if you're counting columns over, just make sure that you start counting with 0. In this case, 4 in the second decimal digit is in the fifth column. I do have these columns alternated, highlighted. You can kind of tell that every other column is a little bit darker to make it easier to scroll up and down. We're looking in this column in this row, and the number we find is right here. The area we are looking for is 0.996. So, type this. I'll move this text box in a moment to a better place. How about according? Chart. Area is 0.9969. Thus, the probability that z is less than 2.74, I'll adjust this text box in just a second, folks, is equal to 0.9969 or 99.69%. All right, let's do some here. Do a line break here, and we will move this box right. That looks nice. All right, so according to the Z chart, this area is 0.9969. So the probability in a standard normal distribution that Z is less than 2.74 is almost 100%. It's almost guaranteed, which makes me think that I should have moved, when I was drawing this, that I should have drawn that Z further to the right, since almost 100% of the area should be shaded. It's not difficult to use the Z chart, it just takes getting used to. So let's take a look at a few more examples. Let's find that probability that Z is less than negative 1.13. One thing I will emphasize throughout the class is that drawing a good picture can really help you out. Well, let's see what happens if we draw this picture. First off, let's figure out where to put the Z that we're comparing to. In a standard normal distribution, the 0 is always in the middle. Negative numbers are to the left. So somewhere to the left is negative 1.13 is and to find the probability that we are less than that number, we need to find the area to the left of it. So all we have to do is locate negative 1.13 in our Z chart, and that will tell us our left area. Remember, in the Z chart, the numbers on the inside do represent left areas. That is important. That's why it's in all caps there. So we are looking up, I forgot what it was. Oh, how could I forget that it's negative 1.13? I chose 1.13 because January 13th is my birthday. Happy birthday to me. I'm about to turn 50. Yay. Anyway, so negative 1.13 is the Z-score that we're finding the area to the left of. So let's look up negative 1.13. The 0.3 is in the fourth column, so keep that in mind as we scroll down. Negative 1.1 is right here. So negative 1.1, I forget which column. Well, let's just count it out. This is the 0 column. 1, 2, 3. The highlighted area is the area to the left of negative 1.13. Okay, back here and just answer it. Pretty straightforward. The probability that Z is less than negative 1.13 is I just forgot. World's worst short-term memory. I'll blame it on the fact that I'm almost 50. Negative, 0.1292. All right, 0.1292. 0.1292. Or if we're describing the area, 12.92%. There will be times where we want to answer as percents to represent probabilities, and there are times where we will want to keep it as a decimal because we'll be doing more arithmetic with that number. All right, so far this is pretty okay, but what could possibly go wrong, or rather I should say different, and how do we accommodate that? Let's take a look at another example. This one's going to have a slight twist to it. Let's find the area to the right of negative 0.71. And for clarity, I should say that z equals that, since we didn't say anything about a probability involving a z. Well, first off, notice that I'm not asking you a probability. So we can answer it as a percent, or we can answer it as a decimal. We'll answer it as a decimal. But do you know what the other problem is with this? What is the problem with using the z-chart to find the right area? The problem is that the z-chart will only give us, if I can get it to share, left areas. So how do we take a chart that tells us left areas if we are trying to locate a right area? Well, let's start by looking at the left area. Type this because I can type it faster and cleaner than writing it, if I can get the text box going. All right, here we go. All right, according to the z-chart, area to the left of z equals negative 0.71 is, well, we didn't actually look it up, so let's go look it up. Negative 0.71 is the z-score we're looking for. The 1 is in the second column, so now we just have to find negative 0.7 in the left column. Negative 0.7 is here. 1 is in the second column. Looks like it's 0.2389. 0.2389 is the number that goes here. 0.2389. Widen the text box a little. And let's make sure that I did write the number down correctly. 2389 and 2389. Okay, so, but that's the left area. So, right area is, let's think about it for a second. Now, in order to do this, we have to use a property of distributions that I haven't mentioned yet, although I did casually mention, let me see if it's still there. I did casually mention right here. The total probability has to be 1. Now, how can that help us over here? Well, remembering that area is equal to probability, that means the total area is equal to 1. So if the total area under the bell curve is 1, and we know the area to the left of it, how would we figure out the area to the right of it? Answer. This right area is always 1 minus the left area. Thus, area to the right of z equals negative 0.71 is 1 minus 0.2389, which equals 0.7611. So that's how you find right areas. In fact, I want to go ahead and highlight that because that's an important something that will pop up every once in a while, and it's important to remember that right area is always 1 minus the left area. All right, I'm going to set up another problem. I want to give you a chance to pause the video and see if you can go find the right area. So let's see what that example is. Find the area to the right of z equals, I'm going to erase the 0 in the middle. We're assuming it's there right now, but it's kind of in the way. Find the area to the right of z equals 0.98. So if you have the distribution table opened in Canvas, go ahead and pause the video and go see if you can look up the area. Now, if you didn't pause and try it, I'm about to answer it, so spoiler alert. Right area always going to be the 1 minus the left area. So let's look up the left area by looking up 0.98 in the z-chart. For 0.98, you have to go to the second page, and it's on the screen. You find it. Here's 0.9. Here's 8. And so the left area is 0.8365. 0.8365. Which, if you subtract, is 0.1635. Meaning that in a standard normal distribution, there's a 16.35% probability that a value is greater than 0. All right, I have a challenge for you before we move on. This is not the answer we looked up because that was representing a right area and we were looking for a left area. However, that answer is in the z-chart somewhere. So my challenge to you is to go back to the z-chart, look in the middle somewhere and find 0.1635 and see what its z value is. It might surprise you, but then again, it might not. So to make sure you understand, somewhere in the z-chart is 1635. It's not up here. These are 50% higher, so we have to scroll up. Let's go find it. Now, these numbers aren't random. They're in a certain order. Like on this page, each row is decreasing, but as you move down, the values are increasing. We are looking for what? We are looking for 1635? Yes, 1635. All right, so let's go find 1635. 1635. Looks like it's going to be in this negative 0.9 row. And there it is, 1639. So what is that z-score? Negative 0.98. Negative 0.98. Well, that sounds very familiar. Negative 0.98. We looked up positive 0.98. All right. So there's something going on here. Well, first, let's kind of document what happened. Using the z-chart, we see that 0.1635 is also the area to the left of negative 0.9. Coincidence? I think not. So why would it not be a coincidence? Well, it's because of one of the characteristics of a bell curve. It's symmetrical. Well, hello, Josh. How are you? I'm going to go ahead and admit you. But just to let you know what's going on, and this being the first video, I expected some people to randomly jump in. Hey, Josh, this is Mr. Chapp. I'm the professor of your statistics class. Just to let you know what's going on right now, I'm recording. Oh, Josh is gone. I guess Josh didn't want to hang around. Okay. All right, so using the z-chart, we see that 0.1635 is also the area to the left of, I left out the z equals. Tisk, shame on me. Coincidence? But the answer is no because of the symmetry. In other words, if we were to draw a bell curve with, whoa, that's not what I wanted. If we were to draw a bell curve and look at negative 0.98 and shade to the left of it, then look at another bell curve at positive 0.98 and look to the right of it, these are mirror images. I can type. Never mind, I'll just write it. Maybe. These are mirror images. And because the center of the bell curve is 0, that means the number on the right is just the opposite of the number on the left. And because of the symmetry, that means that the two shaded portions have the same area. So this actually tells you that there's two ways to find right areas. One is to look up the left area and subtract it from 1. The other is to look up the left area of the opposite z-score. I don't care which one you do. I will always look up the left area and subtract it from 1 so that I'm always looking up left areas. I'd like to do one more. Let's find the area problem before we flip this around and do it backwards. Backwards is where you start with the area and come up with the z-score. What's the area between these two z-scores? Between z equals 0.25 and z equals 1.25. Well, remember, our z-chart tells us left areas, so let's think about this. If we look up 1.25 in the z-chart, it won't tell us just this pink area. It will tell us this whole thing right here. I'll shade it in and then undo it. But if we look up 1.25, it will tell us all of that, which is not what we want. So how could we figure out just the pink part? What would happen if we looked up 0.25? That would tell us the area to the left of that. That would tell us this. So here's what we know. The area to the left of z equals 0.25, the orange part, plus the pink part, which we want, is equal to the green part, the area to the left of 1.25, which means if we looked up the area to the left of 1.25 and subtracted the area to the left of 0.25, then it would give us the pink area in the middle. So let's do that. All right. Type this. I'm going to try to type this. It wasn't going so good. Area between z equals 0.25 and z equals 1.25 is equal to area to the left of z equals 1.25 minus the area to the left of z equals 1.25. And both of those left areas are things that our chart can tell us. So to find area between, you look up the two areas and subtract them. So let's look them up, shall we? All right. Let's start by looking up 1.25 because it'll be the larger of the two areas. If we go to 1.25 on the Z chart, I have to go to the second page. And we can actually see it right here, 1.2. Then the fifth column is this one here. Go down to where they intersect. It looks like it's right here at 0.8944. So let's go ahead and write that down. If I can get back to the page. 0.8944 is the number. 0.8944. And again, what that number would represent is this total area left of 1.25, which is more than what we want. Then from that, we will subtract the area to the left of 0.25. In other words, we'll look up this area to subtract it from the whole thing, which will leave us the pink area. And if we go to 0.25 on the Z chart, 0.25 would be in the 0.2 row under the 0.5 column, and their intersection is at 0.5987. 0.5987 is what we were subtracting. Make sure I wrote down the correct number. 0.5987, yes, it is the correct number. All right, so what does this equal? Well, that's just a subtraction problem. This is what calculators are for. So, calculator real quick. 5987. And by the way, I didn't type the decimals because I know this is decimals. 0.2957. All right, so let's quickly review how to find these areas because that's the key move that we're going to be doing in this class. All right, to find the area to the left of something, you simply look up the Z-score in the chart by looking in the left column in the top row and then finding where that column and row intersect, or the desired column and row intersect. To find the area to the right of something, you look up the area to the left and subtract it from 1. And to find the area between two Z-scores, you look up both areas and subtract them. The last thing I want to cover in this review of a Z-chart is how to work a Z-chart backwards. For example, find so this time I'm going to give you a picture and tell you what the area is. Now we got to go find the Z that goes with it. So let's put a Z over here. Don't know what it is, so we'll put a question mark. And let's shade in this area to the right. And let me just go ahead and tell you that this area is, let's use an area of 0.8078. 0.8078. All right, so how do we reverse engineer this? Well, literally work the chart backwards. The information that we're given is an area. The left areas are inside the chart. So we have to go scouring through the chart looking for that correct left area. All right, so we're going to look for 8078 inside the chart. 8078 inside the chart. 8078. Well, they start out pretty small. Actually, before we go looking, let's go back and look at the picture and think about this. I know one thing about the Z. It's got to be positive. Why? Because number one, 0 is in the middle, and number two, it's split in half at the middle, meaning 50% is to the left. We have more than 50% of it shaded. We have 80.78% shaded. So I already know that I'm looking for a positive Z value. So let's just go ahead and go to the positive part of the chart. Positive part of the chart. All right, so going down, we're looking for 8078. There's a guy we had before, don't need him. I would go down the first column until you find a reasonable row to look across. So 8078 is probably going to be somewhere in these two columns, if it's in there at all. And there it is, 8078. So what is that Z-score? To the left, I see 0.8, and on the top, I see 7. So 0.87 Z-score with 0.8078 to the left of it. And that is our Z-score. Really no calculations to do here. Just a matter of knowing where to look and finding the number that you're looking for. So what can go wrong here? Well, a couple of things. Number one, well, let me just put the problem up here and then we'll see. All right, let's say that the left tail area is 0. It's actually not what I wanted to write. 0.0130. We could have done that one, but this is the one I had in mind. Let's say this left tail area is 0.0130, and we want to find the Z-score. We have to find this 4-digit number inside of the Z-chart. 013. All right, so here we are at the top. 0.130. Let's scroll down the left column. Looks like we're going to be in this neighborhood here, 0.130. So let's see, it's not in the top, it's not in the negative 2.3 row. Those are all too small. And as we go across the negative 2.2 row, here's one that's close, 0.0139, 0136, 0132, 0129. Number that we're looking for is not here. Could have done this a long time ago. The number we're looking for is 0.130 is not here. It is, however, between these two highlighted numbers. So what do we do when the number we're looking for doesn't exist? The answer is we choose the closest value. Which of these is closer to 0.130? This guy. And the easiest way to see that is to ignore the decimal and think of it as whole numbers. 132 versus 129. The 129 is closer to 130. It's only 1 away. This is 2 away. So if your area is not in there, then you find the closest one and use that as Z-score. In this case, we would use negative 2.2. Should be 3, but let's make sure. Yep, 3 at the top. Negative 2.2. All right, so that's the moral of that story. If the Z-score you're looking for is not there, then you use the closest one. Excuse me, if the area you're looking for is not there, then you use the closest one. Let's write this down. The closest area is 0.0129. Make that a semicolon. Its z-score is z equals -2.2. All right, so that's issue resolved. If the area is not there, you find the closest one. Raises another issue, as I'll show you in the next example. Let's say you want to find the z-score whose left area is 5%. What is the z? That's the question. Well, since we have an area and the areas are inside of the z-chart, we need to think of this as a decimal. More specifically, we need to think of this as a 4-digit decimal. I'm assuming everybody knows how to turn a percent to a decimal by moving the decimal 2 places to the left. In 5%, it's after the 5. Move it 2 places to the left to get 0.05. But because the areas in the z-chart have 4 decimal places, we'll append a couple of zeros. So we're looking up 0.0500 in the z-chart. Let's go find it. It won't be there. That won't surprise you. Notice I was kind of already scrolling through, but if we were looking up 0.0500, it looks like it should be somewhere in these 2 rows. Those are their first numbers. That's less than 5%, that's more than 5%, so we're looking at these 2 rows. And all the numbers in the top row are greater than 5%, less than 5%, so we need to look at the -1.6 row. And let's look for 5%. 0500. No, too big, closer, closer, getting real close, missed it. I knew it was going to miss it. I did that on purpose. So what do we do when the area we're looking for is not in the chart? We find the one that's closest to it by looking at the 2 that it's in between. But which of these is 5% closer to? The answer is it's dead center. If you ignore the decimals, this is exactly 5 above 500. This is 5 below 500. So our plan of choosing the closest area can fall apart when there are 2 areas that the desired area is exactly in between. So what does that mean we do? We're going to use -1.6, that's the row, but will we use 0.04 or 0.05? There's really no wrong answer here. -1.64 would be okay. -1.65 would be okay. Some people even go as far as to average the 2 and say -1.645. I wouldn't go that far. I do have a protocol that I typically use, but you go back to the, I haven't left it yet. When you are dead center between 2 areas, you can use either of the top values, in this case, -1.64 or -1.65. I will always default to the larger second digit. That doesn't mean you don't have, that doesn't mean you have to. That just means that's what I do. Desired area is exactly between 0.0505, where z equals -1.64, and 0.0495, where z equals -1.65. Give me 1 second to resize the text box. All this on one line. When this happens, you may use either z. The professor, that would be me, will always default to the larger second digit. As such, I would say z equals -1.65. There's a reason why I default to the larger digit. It has to do with confidence levels and significance levels when we do hypothesis testing and confidence intervals, which we will first test. But again, I want to reiterate that if your area is dead center, choose either z. I personally will always choose the larger of the 2 digit, the larger digit in the second place. On a test, I would accept either one as correct. So don't worry about which one you choose. All right. Okay, so that's issue number 1. What happens if your area is not only not in the chart but is dead center? You may use either z-score. I will always use the larger second digit. But there is Well, actually, there's more than one, but there's only one more thing that I would like to show you, and then we'll wrap up this video. For the last example, we're going to find the z-scores that cut off the middle 95% of the standard normal distribution. This is actually a pretty standard thing to do when we're doing inferential statistics, when we're making confidence intervals, which we will be reviewing soon. But what I mean is, if we have a standard normal distribution, let's find the two z-scores that cut off the middle 95%. What are these z's going to be? Well, let's think about what our z-chart tells us and what we currently have. Our z-chart tells us left areas. So if we're going to look up either area, if we want to know the area to the left of the larger z, we would need to know all of this area, which we don't know. We can calculate. But if we wanted to find the left z-score, we would just need to know this area. You know the area of that left tail. Give you two hints. Total area is 100% and the picture is symmetrical. The area of the left tail is 2.5%. Why? Because together the tails, plural, is 100% minus 95%, which is 5%. But one tail, because of the symmetry of the picture, is going to be half of 5%, which is 2.5%. Now, you don't have to write down all the calculations. I was just writing them down so you could see them. But anytime the middle is 95%, then the left tail is 2.5%. Right tail is the other 2.5%, which together make up the remaining 5%. It's not that hard to calculate the area of one tail when you know the middle area. For example, what if the middle area were 80%? The middle area were 80%, then the left tail would be how much? 10%. Because if the middle is 80%, then the two tails make up the other 20%, half of which, of course, is 10%. But in this problem, this left area is 2.5%. But we need to think of that as a 4-digit decimal. So move the decimal in 2.5% two places to the left, get 0.025. And we need a 4-digit decimal, so go on a 0. Let's find this one, and then we'll worry about the other z. All right, we know the left area is 0.0250. Let's go to the z-chart and find it. And hope that it's in here. Looking in the left, 0.025 seems to be between these two rows. Let's see if we can find, whoa, here it is right here. It's in there exactly. Hooray, don't have to pick one. Negative 1.96. All right, so we know the left z is negative 1.96. Equals negative 1.96. Now that we know the left tail, we could figure out the area to the left of the other z, but it's not necessary. Why? Symmetry. If we cut off the middle 95%, then these z's have to be opposites, so the other one is positive 1.96. The next video will be about the t-distribution, and at the conclusion of that video, there will be a homework assignment that won't come from the book, but will actually be typed up in a module, and then there will be a quiz over that homework assignment. Actually, it'll be a little bit different, but the quiz will be in the homework assignment. I'll give you more details once it's ready to go. All right, well, thanks for your time, and if you have any questions, please get a hold of me. I'll left my contact information in here.